Okay, so here we're going to do a couple of examples using the integral test to determine convergence. All right, so the first one is this series here, the sum of n over n squared plus 1. Right, so we see it as it is decreasing, right? The denominator is increasing at a faster rate here. So it'll be a decreasing function. So we again start off by setting up the limit here as t goes to infinity from 1 to t of n, or excuse me, x over x squared plus 1. Dx. All right, and this is a natural log integral, right? If you let u to be x squared plus 1, then du is 2x dx, right? So the only thing missing there is that 2, right? So this is the limit as t goes to infinity, ln of x squared plus 1, evaluated at t and 1, and then we get the 1/2. All right, and then here equals, take the 1/2 outside the limit, ln of t squared plus 1 minus ln of 2. Oh, and the limit, of course. And the limit as t goes to infinity. Okay, so ln of 2 is a constant, so that stays a constant. And then here our natural log is an increasing function. So we see here that this goes to infinity. All right, so hence by the integral test, this series diverges. By the integral test. Okay, so now let's take a look here at a different example. Let's say we had 1 over 2 root 2 plus 1 over 3 root 3 plus 1 over 4 root 4, etc. Right? And I want to determine the convergence of the series. All right, and I'm going to use the integral test. Right? So again, I'm going to need to write this in a summation notation. So kind of looking at this. All right, and again, 1, we can, since 1 root of 1, we can always think of it does follow the pattern, right? Same thing, right? All right, now here it looks like the pattern here is 1 over n, and the exponent here that's happening, right? If we think of, that's 2 to the first, 2 to the 1/2, so 2 to the 3/2, right? So it's n to the 3/2, and starting off at 1 to infinity. Okay, so again, also a decreasing function as n is bigger than 1. So I will use the integral test, setting up from here 1 over x to the 3/2 dx. All right, again, set up a limit as t goes to infinity from 1 to t, x to the negative 3/2 dx. So just writing this in excuse me, writing this using a negative exponent, and then I can apply the power rule here, right? So it's going to be the limit as t goes to infinity. Add 1 here, we get x to the negative 1/2. So times negative 2, right? We divide by the new power, which is negative 1/2, which is the same as multiplication by negative 2. And this goes from t to 1. So we get negative 2 limit as t goes to infinity. Right, I'll factor out the negative 2, and then we get 1 over root t, and then 1 is just 1. All right, so we get this. All right, and notice as t goes to infinity, this root t, since it's the denominator, gets really large, driving that whole term to go to 0. Right, so what this converges to is the finite value of negative 2 times negative 1, which is 2. Right, so what does that mean in terms of our series? By the integral test, the series converges. Right. Now, not to 2, right? In fact, it will, most likely will not be the value of 2, but we just use that integral, the fact that it converges to a finite value, to conclude that the series also converges to some finite value, not necessarily 2. Okay. Now, one more type of example that will show up a lot in our in the next few sections. This general class of functions, which we're going to call p-series. All right, so here we're going to look at what's defined as a p-series. So p-series look like this. This is what's defined as a p-series. So the above example that we did, right, it is a p-series where p is 3/2. All right, and I want to kind of generalize these types of p-series so that now moving forward, when I see a p-series, I know whether it converges or diverges just by identifying the value of p. Right? This will be more helpful when we're dealing with a comparison test, a limit comparison test, because it will allow us to compare it, in a sense, to functions or series that don't quite look like a p-series, but have some similarities, right? For instance, maybe something like the first one here. So let's take a look here. And let's break down different cases for the p-series. Right, now, if p happens to be negative, right, so less than 0, right, and we'll assume that here if it is, or let's just say p is less than 0. So if it's negative, right, then the limit as n goes to infinity of the terms of the sequence, right, if I just look at 1 over n to the p, right, this value will be a whole value, right? It comes up to the numerator, and it really grows without bound, right? So this goes to infinity, right? Think of if p was negative 2, right? So if p was, for example, negative 2, then we get the limit as n goes to infinity of 1 over n to the negative 2, which is the limit as n goes to infinity of n squared, and this is unbounded, right? That goes to infinity. Right, so that would happen for all cases where p is negative, right? And by the divergence test, right, this tells me that it's a non-zero value, so it will diverge, right? So p series diverge for p less than 0. All right, and then there's also a value when p is equal to 1, that's the harmonic series. Right, and I know that this diverges. Okay, so now here, now I bring that up because I want to use the integral rule for the other values. All right, so for the integral 1 to infinity of 1 over x to the p, the only way this is decreasing if p is positive, right? And then I can apply the power rule, except when p is equal to 1, right? In which case that power rule does not apply for integrals, okay? All right, but that's okay because I already established that case. That's the harmonic case, so I don't have to worry for that value when applying the integral rule here. All right, so I'll set up here the limit as t goes to infinity of 1 to t, 1 over x to the p. All right. And then I'll apply the power rule for integrals. Okay, so dx, oops. So if I apply the power rule for integrals, right, we get the limit as t goes to infinity of x to, remember that's negative p plus 1 divided by 1 minus p from 1 to t, right? Okay. All right, so here I'll just rewrite this with 1 over 1 minus p, and we could see why we had to isolate 1 as its own specific case, right? Because 1 here, when p is 1, the power rule does not apply. X to negative p plus 1. Okay, now as we saw before, if I get a positive value for my exponent, that is just going to grow to infinity. All right. Now, if I get a negative value for my exponent, then that's going to go to 0 and it will converge. So we have 2 more cases here, right? So it would converge when negative p plus 1 is less than 0. Right? And the reason for that is because now we're in the case where it's like 1 over x to some power, right? And then it'll grow without bound in the denominator. Right? Think of like if we were to think of the limit as x goes to, or as, right, x goes to infinity here, of x to the negative 3, right? It's 1 over x cubed, right? That grows without bound in the denominator, so it goes to 0. Right? So if I have a negative exponent, then it will converge, right? Because of this relationship. So that means here, subtracting 1, then multiplying by negative 1, or bringing p over to the other side. When p is greater than 1, we have convergence. Now in the other case, when p is bigger than 0, then we're back in the case where we have an exponent that is going to turn out to be positive, right? And then that limit, as n goes to infinity, will also go to infinity. Right, so it converges when p is 0, and it diverges when p is less than or equal to 1. We have divergence. Okay, again, 1 we proved already for the harmonic series, right? We did in a previous video. And then the values from 0 to 1 follow here, as well as all negative values, which was our first case that we discussed, right? So now for any p series, right? Any series that looks like this, I just need to identify whatever the value of p is. If it's bigger than 1, it's convergent. If it's less than or equal to 1, it is divergent.